Welcome everyone, I'm David and I'm going to present you StRoM Smart Remote Memory. In recent years we have seen a rapid increase in the available network bandwidth, while at the same time CPU frequencies have been stagnating. Given these two trends, the gap between the network bandwidth and the compute available on the CPU is widening further and further. As a result, more and more CPU cycles have to be allocated for network processing. This means that we have less CPU time available for the application. This trend is intensified by the use of operating system network stacks that introduce frequent context switches between the application and the operating system. Remote Direct Memory Access RDMA is addressing the widening compute bandwidth gap by completely offloading network processing to the network card. It also enables the network card to directly access host memory. This means both the CPU and the OS can be bypassed, reducing the latency and the load on the CPU. The significant improvements in latency and throughput led to a widespread adoption of RDMA for distributed systems, from key value stores over database systems to distributed graph processing. At the same time, these systems show the challenge of efficiently using RDMA to take full advantage of its properties. To illustrate this, we looked at the example of a key value store get operation and how it can be implemented using either two-sided or one-sided RDMA. In the two-sided case, the client uses the send-receive operations. In a first step, the client sends a GET request to the remote CPU. Then, the remote CPU processes this request by accessing the hash table, comparing the lookup key with the keys in the hash table entry, and retrieving the value from the value store. In the final step, the remote CPU sends the value back to the client over RDMA. As we can see, this client-server model maps very well to two-sided operations and allows us to execute an RPC in a single round trip. The drawback of this approach is that the remote CPU is involved in the operation, introducing additional latency. In case of one-sided, the client makes use of the read operation to directly read from remote memory. In a first step, it reads the hash table entry using an RDMA read operation. Once it retrieves that entry, it checks it against the lookup key to determine the address of the value. It then issues another RDMA read operation to retrieve the value from the value store. We see that in the case of one-sided operations, the remote CPU is not involved, fully benefiting of the low latency that RDMA is known for. The drawback is that the two round trips are required to implement the GET operation, and potentially more if we consider misses or other failures. In summary, there is no clear winner when it comes to two-sided versus one-sided operations, and many factors have to be considered when picking one over the other. With StRoM, we are introducing a third alternative that addresses these drawbacks. StRoM allows the application to directly deploy acceleration kernels on the remote NIC. Since StRoM is built on top of RDMA, the kernel can directly access the host memory. It can also transmit and receive data over the network using RDMA. I will now show you how we can implement the GET operation using StRoM. As you can see, we implement the GET operation as a StRoM kernel and deployed it on the remote machine. As a first step, the client invokes an RPC on the remote NIC using the RDMA RPC command. This command contains the required parameters for the operation. This request is then processed by the GET kernel, which accesses the hash table in the host memory to retrieve the hash table entry. It compares the keys in the entry with the lookup key, and based on this determines the address of the value. Once it retrieves the value from the value store, it can then finally send the value back to the client using a one-sided RDMA write operation. By enabling one-sided RPCs, StRoM combines the benefits of two-sided and one-sided operations. Specifically, we can execute the GET operation in a single round trip without involving the remote CPU. This example has shown us how StRoM can be used to accelerate data access by deploying and invoking RPCs on the remote NIC. In the same way, operations such as the traversal of remote data structure, consistent access of data objects, or the manipulation of simple data structures can be accelerated. Given the powerful architecture of StRoM, kernels can also be used as bump-in-the-wire accelerators for data processing when data is received or transmitted. This includes operations such as data shuffling, filtering, pattern detection, aggregation, compression, or the gathering of statistics. We are looking at an example of this type of acceleration on the next slide. To illustrate the bump-in-the-wire acceleration, we look at the use case of gathering statistics on the fly. We implemented a hyperlocal kernel that can estimate the cardinality of a dataset. The cardinality is a valuable metric that can augment the decision-making of an optimizer in a data processing system, such as picking the optimal algorithm for a given operation. The implementation of the hyperlocal kernel is fully pipelined, such that it can keep up with the data rate of the network. In this setup, the hyperlocal kernel operates on a dataset that is received. While data is being received, it is written to the host memory and at the same time streamed through the hyperlocal kernel. The kernel continuously updates its internal state. Once the complete dataset is received and written to the host memory, the kernel will write its cardinality estimation also to the host memory, making it available to the application running on the CPU. This example has shown that if properly designed, a data processing kernel can execute useful work without affecting the transfer over the network. To evaluate StRoM, we implemented our own FPGA-based prototype RDMA NICs. The Rocky stack deployed on our prototype NICs supports one-sided RDMA operations. We additionally extended it with 2 more commands to support StRoM kernels on the NIC. The architecture of our StRoM NIC is quite flexible and supports network speeds from 10G up to 100G. First, we look at the evaluation of the get kernel previously introduced. In particular, we compare the latency of using one-sided RDMA read to implement the get operation versus deploying the StRoM get kernel on the remote NIC. In the graph, we report the latency of executing the get operation for different value sizes. Independent of the value size, using the get kernel reduces the latency by around 5 microseconds. The difference in latency can be explained by the difference in round trips, which are 2 round trips for the RDMA read and a single one for the get kernel. Secondly, we look at the performance of the hyperlocal kernel. This kernel was designed to maintain line rate processing for networks up to 100 gigabits per second. In this graph, we show the throughput of executing a basic RDMA write operation in comparison to writing the data to the remote machine and processing it at the same time by the hyperlocal kernel. As expected and by design, the hyperlocal kernel does not affect the throughput while doing useful work. With this, I'd like to conclude this presentation. StRoM allows the deployment of acceleration kernels on the NIC, providing data access and data processing acceleration. The flexibility of StRoM kernels makes them suitable for a wide range of operations and applications. A core piece of StRoM is its FPGA-based RDMA implementation, and to our knowledge, it is the first RDMA implementation made available as open source. Given that, we hope that StRoM will facilitate more research in this area. You can find the StRoM source on our GitHub repository. Thanks for your attention.